Welcome back. The last couple of classes, we discussed quite a bit about fundamentals of spin physics and basic important parameters concerning the spin physics to understand what happens to the nuclear spins in a magnetic field. We understood spin angular momentum, spin quantum number, magnetic moment, interaction of the magnetic moment with the external magnetic field, what happened to the magnetization when you apply a radio frequency pulse, how to detect signal, various aspects we discussed. Now we have to proceed further. Here afterwards, we'll start interpreting the NMR spectrum, for which we need to understand some of the important parameters. We start with chemical shifts today. Let us consider a hypothetical situation. A hypothetical situation like this: a molecule which has NH2 protons, CH proton, and CH3 protons. Remember, I told you in the last class, again I'm repeating, in the NMR jargon, if there is hydrogen, if you say proton, it refers to hydrogen. So if I say NH2 protons, that means I am talking about these two hydrogen atoms. So there are three different functional groups present in this molecule. Now, place this molecule in a magnetic field. We want to see NMR of this. Recall my basic condition which I discussed for the resonance condition in NMR. This was given by nu is equal to gamma into B naught over 2 phi. Of course, now I am talking about the protons here. I simply plugged it as resonating frequency of the proton. Gamma is the gyromagnetic ratio or the proton. B naught is the magnetic field, and of course 2 pi. In this molecule, you can also study nitrogen 15 NMR, nitrogen 14, carbon 13, O17, various NMR active nuclei are present in this molecule. But for the discussion to continue, I am concentrating on only protons. Hence, my basic resonance condition I have written like this: nu h is equal to gamma h into P naught over 2 pi. Now, if you proceed further in this molecule, according to this equation, do you find any distinction between different protons present here? This is a general equation. It does not say the resonating condition, whether it is for NH protons or CH proton or CH3 protons. This equation does not distinguish any of these functional groups. Then what does it mean? According to this equation, if I go by this, the resonating frequency for NH2 protons, CH proton and CH3 protons, all the three are same. That means there is no distinction between any functional groups as per this basic equation. Then what I am going to get? If I take the NMR spectrum, I must get a single peak for this molecule, single resonance frequency for proton. I took the simple example of a small molecule. Of course, you can take any molecule of your interest. It could be even a very big protein molecule, any big biomarker molecule, does not matter. Now, as far as this equation is concerned, with our basic understanding, whatever the molecule you take, there may be any number of functional groups present here, any number of protons present in that molecule. I must get only a single peak for proton NMR. If that is the case, NMR would be of very little interest for us, because the interest of the NMR is not just observing one single peak for any given molecule. Then remember I said NMR is an ubiquitous technique which is used in various branches of science. This NMR utility would not have been there and the interest would have died down long ago. So the question comes, what makes NMR a very powerful technique? Let us answer this question now. For this, we need to consider few nuclear spin interactions. What are the nuclear spin interactions? I can broadly classify them into two types of interactions. One is external interaction, other is internal interaction. Now the question is, what is an external interaction? Of course, we all know this. I have been discussing this since last several classes. First external interaction is, you must remember, I said, moment you put the magnetic moment, that is the nuclear spin, in a magnetic field, there is an interaction of this nuclear magnetic moment with the external magnetic field. You please remember my basic equation I wrote. E is equal to minus mu dot B naught I wrote, where magnetic moment was interacting with the magnetic field. This is an external magnetic field. As I said, NMR spectroscopy requires a huge external magnetic field. And this was the first and foremost external interaction, which we have already discussed, which we also called as Zeeman effect. This is a Zeeman interaction. Second, you remember, you put the sample in a magnetic field, the spins get aligned. That's fine. That is the first external interaction. And we understood what is magnetization, everything, bulk magnetization. But we also discussed, for the detection of the signal, we have to perturb this. We have to create a non-equilibrium situation because bulk magnetization will be thermal equilibrium, so it is static. I said we applied a radio frequency signal in a direction perpendicular to the static magnetization, and we tilted the magnetization from the assumed z-axis, which is the direction of the magnetic field, to the xy plane, either x-axis or y-axis, depending upon the pulse we apply. What is this interaction? It is the interaction of the radio frequency with the nuclear spins. What is after all a radio frequency? It is nothing but an electromagnetic wave, radio frequency signal which you are applying, radio frequency pulse I am sending. It is nothing but a electromagnetic radiation which has electric component and a magnetic component. Now the magnetic component of this is also interacting with the nuclear spin. It is like bringing two magnets together. There will be an interaction. So this we are sending the radio frequency signal from outside. Hence, I call this external interaction. So these two external interactions, that is Zeeman interaction and interaction of the radio frequency with the nuclear spins, we discussed in couple of previous classes. In addition to this, there are other type of interactions which are internal. Internal, I mean within the molecules. You take any molecule of your interest, within the molecule there are several other internal interactions. These internal interactions also we have to understand. So far we have not discussed any of them. Then the question is, what are these internal interactions? This again, I have written four types of interactions. One is the chemical shift. Most important interaction. Okay. We will go and understand all these things detailed. Today, in fact, especially we discussed a lot about chemical shifts. This comes because of chemical environment, electronic charge distribution at the site of a given nucleus. That is one type of internal interaction. Second, it is scalar coupling, also called J coupling. What is this? Remember, when we have a molecule, we have chemical bonds. Consider a molecule. Let us say I have a CH proton here. I have another CH2 proton in between. There is one chemical bond. There are some other substitutions outside. Let us not worry. The proton of this CH can interact with the proton of this CH2. These two protons and this proton can interact because this nuclear spin we can take a tiny magnet, this nuclear spin we can take a tiny magnet, and these two can interact where the medium of interaction or the magnetization transfer is through covalent bond. So this scalar interaction or scalar coupling, also called J coupling, is because of covalent bond. Covalent bond mediated interaction between two nuclear spins. Please remember this. This is again internal to the molecule. We can also think of another type of interaction called dipolar coupling. What is this dipolar coupling? For this scalar interaction, we required chemical bond. Think of a situation, there is no chemical bond. A big molecule is there which in a three-dimensional conformation, there are two protons which may be separated by several bonds away. Doesn't matter. But when you see them, spatially, they may come close to each other. Very close, within 2 or 3 angstroms or 4 angstroms, let us say. They come close in space. But then remember, again two magnets coming close in space. There can be direct interaction without invoking chemical bond. This is spatial interaction. Interaction between two nuclear spins or two magnets through space. And you can understand, because it is a through space interaction, the spatial proximity is very important. When you bring the spins closer and closer and closer, interaction becomes stronger and stronger. As you go away, the interaction reduces. It is distance dependent interaction. Okay, because this interaction is taking place through space. Just imagine two magnets are there. You keep one magnet far away, other magnet far away. There won't be any interaction. As you bring closer and closer and closer, and you become very close, you have seen it. You know, you would have seen in your school days or early college days, these two magnets, when they come close, there is an interaction, either attraction or repulsion, depending upon the way you bring it closer. That is another type of interaction between the nuclear spins through space called dipolar coupling, dipolar interaction. Okay, and this is orientation dependent. Remember, this depends upon the orientation. We'll discuss more when we go to coupling interactions. All these three parameters pertain to spin half nuclei. There, I'm talking about spin half nuclei. But we can consider nuclei whose spin greater than half. For example, we understood nitrogen 14, which has a spin 1. We calculated that in one of the classes. Take deuterium. The spin is 1. And such nuclei, I told you, they are quadrupolar nuclei. And that type of nuclei whose spin greater than 1 can have an internal interaction which is called quadrupolar coupling. Remember, I have mentioned 4 different types of internal interactions. These 3 corresponds to pertains to spin half nuclei, and this is for spin greater than half. Of course, all interactions will be present for this. Not that they for spin greater than half, these three are absent. No, everything will be present. Only for spin half nuclei, this is absent. Please remember that point. Now, these internal nuclear spin interactions, again, I can classify into two types. One type of interaction is called magnetic interaction. Other type of interaction is called electric interaction. What are these electric and magnetic interactions? These magnetic interactions can be further classified as chemical shifts and spin-spin couplings. The electric interactions are for those nuclei whose spin greater than half, that is a quadrupolar interaction. Please remember, in the previous slide, I said 4 different types of interactions, internal interactions, out of which the quadrupolar coupling coming because of the nuclear spin, which is greater than half, is electric interaction. This is the only electric interaction. All other remaining 3 interactions which I mentioned, internal interactions, are magnetic interactions. Okay. Now, if I go further, this internal interaction, magnetic interaction, like for example, chemical shifts, can be further divided into 2 types. One is isotropic chemical shifts, other is chemical shift anisotropy. That means the chemical shift has 2 parts. One is an isotropic part, other is an anisotropic part. You understand? Remember, all parameters in NMR can be expressed as tensors. We can define them as tensors with a 3 by 3 matrix having 9 elements. We can define them. And all these parameters are anisotropic in nature. That means the value of this parameter, which you measure in different directions, will be different. It is not same in all the directions. That's what happens. All parameters in a number, for example, chemical shift has isotropic component and anisotropic component. I'll tell you why isotropic component comes later. And then similarly, spin-spin coupling. This can be further classified into scalar coupling and dipolar coupling. I already told you the scalar coupling is one which mediates through covalent bond, whereas dipolar coupling is through space interaction. This is what I said. Strictly, if you start going analyzing further, the scalar coupling also has an isotropic part and anisotropic part. It is the isotropic J coupling, and also J anisotropy is there. I'm not classifying further, it will become too complicated for you at this stage. You don't have to worry. Similarly, the dipolar coupling is also there. That again we can divide into 2 parts. We'll not go into more details, but remember, broad classification is chemical shift as isotropic part and anisotropic part. Similarly, spin-spin couplings I have classified as scalar coupling and dipolar coupling. Now I concentrate on spin-half nuclei. Basically, in this course, we always concentrate on spin-half nuclei. We don't go to spin one nuclei, only in special examples to understand the coupling of spin-half nuclei with spin one nuclei. I take some examples and interpret the spectrum later. But at the moment, for most of our discussion, we concentrate only on spin-half nuclei. When it is spin-half nuclei, what did I say? This electric component coming electric interaction coming because of the quadrupolar coupling must be 0. It should not exist. True, that will disappear. So for spin-off nuclei, the electric interaction is 0. We have only magnetic interaction, which already I have classified as 2 parts, chemical shifts and spin-spin coupling. Again, I showed you in the previous, we have isotropic and anisotropic parts of chemical shifts, spin-spin coupling, scalar coupling, and dipolar coupling. Okay. So this again I told you we have isotropic and anisotropic parts. All those things we can discuss. But again, depending upon the state in which we study the NMR, whether it is a liquid state, state of the molecule, whether it is in a solution state, whether in a solid state. What happens if you put the molecule in a solution? Let us say I take some dissolve water soluble molecule. I'll take in water and dissolve. It completely dissolves. At any given instant of time, let us say, there will be thermal agitation going on, rapid tumbling motion of the molecules. There is some sort of emotional averaging. What happens in that case? Certain parameters disappear. What are these parameters which disappear? See, when I go to the solution state, when I take into account the emotional averaging, the anisotropic part will disappear, because I told you the anisotropy means you measure the value in different directions. When there is a rapid tumbling motion going on, when the averaging of the motion takes place, all this anisotropic part goes to zero. You will not see this effect in the NMR spectrum in the solution state. What about the dipolar coupling? The dipolar coupling, as I told you, it depends upon the direction of orientation of internuclear vector. It is a orientation dependent. That means when there is a motional average, it is all possible orientations present. That means when you take the average, this dipolar coupling also goes to zero. You understand? In the solution state, anisotropic parts of these interactions goes to zero. Similarly, scalar coupling anisotropy also goes to zero. Dipolar coupling goes to zero. Chemical shift anisotropy also goes to zero. Then what are we left behind? We are left behind only two things: isotropic part of the chemical shift and scalar coupling, that is J coupling. Remember, when I go further, when we discuss scalar couplings, I'll tell you all those things. The very fact it is a scalar, the word it is saying, it is not orientation dependent. That is the reason why this through space, through covalent bond mediated interaction, the scalar coupling, which is mediated through covalent bond, is not going to be averaged out in solution state. This motional averaging has no effect on the scalar coupling, that is covalent bond mediated coupling. That is why it is called scalar coupling. We'll talk about it later. So these are the two parameters which we are left behind. Again, when I go to the solid state NMR, maybe at the last one or two classes, I will briefly give you an idea, because it is not the aim of this course to give in-depth information about solid state NMR. I'll touch upon some of the principles and applications where you try to use them. In that solid state where there is no motional averaging, all these interactions are present. Okay. Now in the solution state, we'll talk about only these two parameters. Okay. With this information, with the discussion what we have, we will start looking pictorially about various types of interactions and their strengths. I said external interaction. There are two types. Internal interactions. There are four different types I explained. Now you may ask me a question: which has a more interaction strength? Among the between the two external, which is more? And among the four internal interactions, which is stronger? Which is dominant interaction? And between external and internal, which is dominant? These questions can be asked. Okay, first we'll understand The external interaction, the major interaction is what? It is interaction of the magnetic moment here with the external magnetic field, the strong magnetic field we are going to put. This is the magnetic moment, the spin of the nucleus, and it interacts with B naught magnetic field. Why I say it is dominant interaction and interaction strength is very large? This is a major interaction. You remember, we calculated the energy in one of the previous classes. We even calculated the frequency. This will be of the order of several megahertz. Separation energy is so energy separation is so much. When we calculated the frequency, it is of the order of few hundreds of megahertz. Then what about other interactions? Radio frequency interaction, which is very small. Among the two internal interaction, external interactions, this interaction is dominant. It's fine. Now let us look at the sources of internal interaction for spin half nuclei and which is dominant. We'll come to that later. First, chemical shift. As I said, this chemical shift is arising because the nuclear spins are not bare spins. Okay, they are not simply bare spins sitting. The nucleus is surrounded by electrons. The electron, mind you, I told you, it has a spin. You can treat like a tiny magnet. Again, there is an interaction going on. As a consequence of the charge distribution at the site of the nucleus, there is some interaction that causes some effect on the NMR spectrum. That is what we are going to understand today. Is called chemical shift. And of course, between two magnetic moments, but that is two between nuclear spins. Remember, I told you in earlier class, we say spin, magnetic moment, and all those things. There's several jargons we keep changing and while using, but everything is same. If I say two magnetic moments, fine. If I say interaction with two nuclear spins, fine. There's no difference between these two. Okay, this through covalent bond can take place. I told you this is called indirect coupling or scalar coupling, also called J coupling. And the next one is the dipolar coupling, which I said is a through space interaction. I say in these two, in between these two spins, there is a covalent bond here. Here there is no covalent bond between this and this. The interaction is going through space. This is through space interaction. This is called dipole coupling. It's dipolar coupling. Nuclear spin is a dipolar if I consider spin of nuclei. Remember I told you it is a dipole. For spin of nuclei, this is a dipole. And this dipole-dipole interaction is there. This is directly taking place. This is called direct dipole coupling. Dipole-dipole coupling. Okay. Also called dipolar coupling. This is given by Dij. This is Jij. The coupling between two spins I and J is Jij. This is dipolar coupling between two spins through space is called Dij. Of course, you can use different notation, but colloquially, most commonly, Dij is the direct coupling is referred to. Of course, next one I said is spin greater than half. It is the electric interaction. Here we have a quadrupolar spin that we are not anyway discussing this. This is an electric interaction when the nuclei have spin greater than half. This is also dominant interaction. Now, this is a picture which is taken from Book of Spin Dynamics, Basics of Nuclear Magnetic Resonance by Malcolm Levitt. Fantastic, very beautifully he describes many things, many concepts in that book. I suggest all of you please go through that book. It is a book worth reading and worth possessing. A lot of things have been discussed by he is one of the pioneers of NMR. You must read that. Now, he has given various types of elliptical or circular shapes, whatever you call. This is a bigger one. Bigger the size, larger the interaction. Remember, this is very big, the quadrupolar coupling. And this coupling strength is of the order of several megahertz. It can be of the order of few tens of megahertz. Sometimes it can be 1 mega, 2 mega, 50, 30, 40, 50 megahertz also. The interaction strength can be very large. But most of the cases there are special nuclei where the quadrupolar interaction, that is electrical interaction, overtakes external Zeeman interaction. That's possible. But that there are special type of nuclei if you study that. Okay, in other cases, we are looking at these type of interactions. Of course, this I told you, quadrupolar interaction is quite large, but in the general cases, what we are dealing with in the solution state, this is a perturbation term. That is a small term compared to Zeeman interaction. Remember, this is a small term compared to Zeeman interaction. We treat this as a perturbation term. So this is quadrupolar perturbed Zeeman. If this is very, very large compared to Zeeman, then Zeeman perturbs this. Will not go more into the details of that. And the J coupling, as I said, through covalent bond, is of the order of few hertz. It can be 5, 10 hertz between protons, few tens of hertz, few hundreds between two different heteronuclei. This is of the order of few hertz to hundreds hertz. Dipole-dipole interaction, that is the through space interaction, is of the order of several tens of kilohertz. Okay, that's very important. It can go from kilohertz, 10, 20, 30, 40 kilohertz could be there, depending upon the orientation, the ordering. And chemical shift is of the order of few kilohertz, 5 to 10 kilohertz, depending upon the type of nuclei. Or it can be very large. If you go to some exotic nuclei like cobalt and others, you can have about 50, 60 kilohertz like that. Much more. Okay, so this gives a rough idea about the strengths of different type of interaction. Since we are not dealing with this, we are dealing with only these things. Of course, in his book, he has introduced spin rotation interaction. I am not bothered about it right at the moment. We are concentrating only on chemical shift, J coupling, and dipole coupling. And among this, dipole coupling has larger strength, then chemical shift, then comes J coupling. Remember this. Sorry. Now, of the three things, there are two very, very important parameters which are extensively used by chemists. That is chemical shift and J couplings. These chemical shifts arise because of different electronic environments around the nucleus. I told you already. See, this is again the picture from Professor Malcolm Lewitt's book. See, in the magnetic field, the nuclear spin is not bare, surrounded by electron. This is going to shield this nucleus. We'll see about chemical shift shielding now. And this J coupling again, there is a magnetic field because of the electrons surrounding it through bond. This goes to through bond and finally goes to this. This arises because of magnetic interaction between two nuclear spins mediated through covalent bond. Remember this. And there are other measurable parameters I told you. One is a dipolar coupling, that is through space, which is a pairwise interaction of spins. That means there are n number of spins possible in a molecule. N number of protons or even heteronuclei is present, let us say. Each spin can interact with all the remaining spins depending upon their spatial proximity. You understand? When we go further, we will understand later. The previous interaction, scalar coupling, has certain strength. Beyond a certain number of chemical bonds, the strength drastically decreases, and after a certain number of bonds, you don't see it. Whereas here, there may be n number of nuclear spins, no problem. One can interact with the others so long as there is a spatial proximity between them. Okay, the number of bonds they are separated does not matter. Spatial proximity is important. And of course, this is a quadrupolar coupling with spin greater than half. I will not discuss this. Now we will worry about chemical shift. How does it arise and what is going to happen? We'll discuss this in the next class.